Hi there. Welcome to Lecture Series 1. This is Lectures with Hrushi. I'm Hrushi. Our first series here is talking about life and climate change. So this is Lecture 1. Today we'll be talking about life on Earth. The next lecture we'll be talking about evolution. Lecture 3 will be about extinction. Lecture 4 will be about the greenhouse effect. Lecture 5 will be about effects of climate change. And the Lecture 6 is there hope and mitigation in general. So before we start talking about life on Earth, of course, we'd have to first characterize life on Earth and kind of define it. So there are 7 characteristics of life mainly. Obviously, there's other ways to define life, but these are kind of the main characteristics of life and main ways to define life. There's order, response to stimuli, reproduction, growth and development, regulation, homeostasis, and energy processing. So a if anything has these 7 characteristics, it is said that it is a living thing. So order, is things that ordered in cells. you know, Um, Within a single cell, there's order in the organization of the organelles within a cell. Response to stimuli obviously is when you cut yourself, your body works to kind of fix the cut. Reproduction would be kind of growing, making your cells mutate. That in that kind of realm. Growth and development, you're not the same person that you were when you were a child. Obviously, you've grown, you've gotten taller, um, things like that. Regulation, kind of just going through regulation, homeostasis, kind of just going through your regular life and just kind of maintaining um, balance, equilibrium within your body. And last is energy processing, so being able to convert food and water and things like that to energy. So these are some characteristics of life. This will come up later when we talk about interstellar life and interplanetary life. So just remember these things. These are important characteristics of life. So there are also boundary cases for these definitions. So this picture that we have here on the right is obviously COVID-19, the virus. So viruses are special. They're very controversial as to whether or not people consider them to be living things or not, because they do possess some of those 7 characteristics and they don't possess other ones. So I'll leave it to a thought question for you to figure out which ones they possess and which ones they don't possess. So now we go to the topic or answering the question, why is there life on Earth? Why Earth? Why not other places? So there's 4 main reasons for why there's life on Earth specifically. First one is the habitable zone. Specifically, we are in the habitable zone. Second one is our atmosphere. The third one is liquid water on our surface. And the fourth one is our magnetic field. So our first reason that we have here is the habitable zone. So what is a habitable zone? It is this region in the, kind of like it's a region within the orbit of a star where the temperature and the conditions are just right. Uh, in this picture, you can see that it's this green area here. So anything closer to the sun or a star, this doesn't have to be just our our star. It can be any star. Anything closer than this green area would be too hot. Anything farther away would be too cold. So Earth, we lie in this habitable zone. So what does that mean if we're in the habitable zone? That means that we get just the right amount of light and warmth for life to exist and life to thrive. And this habitable zone, is different for every star. Obviously, depends on the size, the brightness, the temperature of the side of the star, and uh, so the planets that are in the habitable zone for every star might not be the same from star to star. The location of the planets, it could be if the third planet on some star is in the habitable zone, it may not be in the habitable zone for another star. Maybe the seventh or eighth planet would be just right for that star. So this, first we'll talk about this diagram on the left here. This is a very, very famous graph in astrophysics and astronomy called the Heartspring-Russell diagram. So two astrophysicists, Heartspring and Russell, they individually came to this uh, graph that's given here. And what they realized is this graph actually is the timeline, the evolution of a star. So up here in the top left would be the birth, kind of like the early stages. And this entire area here, let me annotate real quick. This area down here is called the main sequence. So what does main sequence mean? That means that is the lifespan of a star. So it starts here and it goes down, 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 and it gets, this is the adult life of a star. But and this is 90% of its life. So about 90% of a star's life is spent in this main sequence area. And the x-axis here, I know it's kind of grainy, but the x-axis is surface temperature. The y-axis is the luminosity. So kind of the brightness scale. Um, I believe that is in watts. Um, so the kind of the same unit of measure as a light bulb. How much brightness a light bulb gives. It's kind of similar to that. So how much brightness is given off from a star. And then this area up here is kind of the old. When they become old, they go up here. They become really, 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 really big. They become into giants and super giants. So our star was actually it'll actually be a red giant. So probably somewhere in this range it'll be. And you can actually see here in this diagram it says red giant. So that's what it'll be. It'll become a red giant. Um, yeah, and then once it dies, it goes down here and becomes a white dwarf. So this white dwarf area is actually dead stars. So this is old stars up here. This is the adult life main sequence, 90% of its life, and this is the dead stars, white dwarfs. And they become really, really small, sometimes really bright, usually not really bright because you see the luminosity is pretty low, but they can have pretty hot temperatures, as you can see from here, this diagram. So as you can see, from because of this, the lifespan of the star, um, once it goes down the main sequence and kind of just like finishes its adult life, it becomes super super big, right? So over the course of our sun's lifetime, the sun is getting a little bit bigger, 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 and eventually it'll just erupt into this super giant, or I guess it will not be a super giant, it will just be a regular red giant, but it'll become a giant. And that means that our sun is getting bigger. So the habitable zone is actually shifting outwards. So it's moving towards Mars and Jupiter. So what does that mean? That means that the habitable zone of a star is not always in the same place for the entire duration of the star's life, which is pretty cool. So we just happened our planet just happened to be in the habitable zone um, when life was beginning to start, and it really helped out. So yeah, it might our star will or our planet will not always be in the habitable zone. Erase this real quick. All right, next slide. So the second reason that there is life on Earth is because of our atmosphere. So we will begin by talking about the origin of the atmosphere. So how did the atmosphere start? So the main kind of theory is that asteroids came and hit our Earth. They completely bombarded our Earth. I believe it was a time called the heavy bombardment. That is what I believe was called in the early solar system formation. So the first kind of few million billion years, couple million years maybe. Not sure about the timeline for that. It's called a heavy bombardment where asteroids just hitting everything. And that's actually one of the theories of how the moon was formed, is that an asteroid that was super super big came, smashed Earth, and just an entire chunk of the Earth went out, and that chunk was actually big enough that its own gravity was able to make it spherical and in the shape of the moon. And because the Earth is obviously rotating, its own gravity was able to kind of fix itself and become kind of sphericalish again. But if you know a little bit about astronomy, you know that the Earth is obviously not a perfect sphere. It's a little oblate, a little more like a kind of a deflated beach ballish kind of shape. It's not a perfect sphere. Um, so yeah, the origin of our atmosphere would be this during this heavy bombardment with the asteroids were just hitting our Earth. It was degassing the Earth's crust. So what does that mean? That means that when it hit the Earth's crust, it actually released all this gas. It released gas every time it hit it, maybe through volcanic eruptions, or just buried gas under the crust of the Earth, which is the outermost layer of the Earth's surface. Was able to basically release all this gas up, and this gas was able to build up and basically form our atmosphere. And our atmosphere is actually so thin that if our Earth was simulated by a basketball, if you were to wrap around a small piece of paper around just a piece of regular piece of paper, if you were to wrap around a piece of paper around the basketball, that would encapsulate 99% of our atmosphere. So it's super, super small relative to the size of our Earth. Um, and how is our atmosphere maintained? Like all this, it's built up, but how's it there? Like, won't it just like fly away? Won't the um particles, the gas particles just fly out into space? Well, how is it there? So it's actually maintained through this really cool kind of thing called hydrostatic equilibrium. So this means that there's a balance of the gas pressure forces and the gravitational force. So this diagram kind of shows it really well. The gas pressure would be the pressure exerted on the kind of the atmosphere layer by the gas, and I guess the Earth's crust too. It's the pressure. So like when a gas particle hits that thing, it's applying a little bit of pressure. So it's that pressure, and it's a balance of that and the gravitational force of Earth. So it's the same force that is keeping you sitting in your chair, or keeping you sitting on the ground, or whatever you are. It's the same force that's keeping us in place. So it's a balance of those two forces that actually allows us to have an atmosphere, and the atmosphere to not fly away. And actually, interestingly enough, this kind of the related force of hydrostatic equilibrium is actually the same reason that our sun is not collapsing right now or expanding and swallowing us whole. Next slide. So just to reiterate, kind of um, the maintaining of gas particles in our atmosphere, and why the gas particles don't just fly away. It's kind of this rule of thumb approximation kind of thing, um, with just a little bit of physics. You can get this equation that's basically saying the velocity of the gas particles, which is basically just speed with a direction. Um, so this velocity of the gas particles has to be less than or equal to the escape velocity of the planet divided by 6. So what is escape velocity? Escape velocity is the velocity needed for a particle to be able to kind of leave the uh, gravitational influence of a body. So I I believe, if I'm not mistaken, it's around 11 kilometers per second for Earth, and if I am not mistaken, I believe the equation for escape velocity is the square root of 2 g over r. So g is just a constant. It's called a gravitational constant, 6.67 times 10 to the power of negative 11, I believe. M would just be the mass of the body. So in this case, when we got 11 kilometers per second, we just took the mass of the Earth. And R is just the radius of the Earth, or the radius of the body, planet, moon, whatever. I believe this is the right equation for that. So that's what escape velocity means. So in order for gas to be in the atmosphere, and in order for it to not escape our atmosphere, it has to have a velocity that is less than or equal to a sixth of the escape velocity. So helium and hydrogen and all these particles must have like a smaller velocity in order for it to be able to stay in our atmosphere and not fly away. which is just it's just a really cool equation and a really visual way to represent this, or mathematical way to represent this. Ugh. All right. Now, lastly, the reason that there's life on Earth. So all this built up to kind of this part is the ozone layer. So the ozone layer, which ozone is O3, as written here, O3. So all know H2O water. It's two hydrogen and one oxygen. So that oxygen, if there was just three oxygen, bonded together, then it would create the molecule ozone. So the ozone layer is basically a buildup of ozone in our atmosphere. I believe it is near the stratosphere. I'm not too sure on that. But the ozone layer, basically, why it's so important is because it absorbs the harmful UV radiation given from the sun, and it actually is able to convert it into thermal energy. So that means that it takes the UV radiation so that the life on the earth would not be exposed to this harmful UV radiation, and it basically uses it and converts it to thermal energy, which means it uses it to keep the earth warm, which is really cool. So it is actually able to give us a really nice warm temperature. Um, as you can see from this diagram, not all the UV radiation obviously um, is absorbed by the ozone layer. UVC, UVB, mostly UVA here, which are just three different types of UV radiation here. UVA is basically able to pass freely through, but it's basically absorbs a lot of the UV radiation, and without this, we would just be getting bombarded by these UV radiation from the sun, and we would basically not be we would not be able to live or reproduce or have those characteristics of life. We would not be able to evolve if it was not for this ozone layer. All right. And a result of the ozone layer and our atmosphere is actually liquid water on the surface. So this is our third reason as to why we have life on Earth is liquid water on the surface. So if you look at this diagram, you can see all of the planets. We have Mercury here, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. You know, what is different? What makes us special from this? It's very, very clear from this that we can see that our planet is the only one that has liquid water on the surface. And so far in our solar system, Earth is the only one that has liquid water on the surface. There are other, planets that have water, obviously, but it's not liquid. That's the most important one. It needs to be liquid flowing water on the surface. In other planets, like on Mars, there's polar ice caps. So they have it in the form of ice. Um, and in some of the moons of Saturn and Jupiter, there's also ice caps. And actually, in one of the moons, I think of Saturn, I cannot remember. There's actually evidence to suggest that there is a subcrust or under the surface of that moon, there is a whole ocean. And they don't know if that ocean is water or if it's methane or if it's something else, but um, Earth is the only one that has liquid water on the surface. So that's what makes us special. And that's what allows us to basically give life to this kind of the origin of life is this liquid water on the surface. And it is a result of the combined effect of having an amazing atmosphere that keeps us warm and also being in the habitable zone that gives us that light and warmth, that perfect balance. And all of this together creates the perfect temperature for liquid water to exist on our surface and not be blown away by space and everything that happens in space and space weather and just and why is this important? Why is water important? It's because so far all known forms of life, see, I put known in italics because we don't know any other form of life that can exist without water. And that is important because there might be other forms of life that don't rely on water, that have evolved to maybe use methane as a form of energy production, you know? So we will discuss more on that topic when we get to the interstellar and interplanetary life unit. But just know that water is super, super important for our current understanding of life in our universe. Now, our fourth reason. Oh, looks like I forgot to erase this. And our fourth and last reason as to why there is life on Earth is because of our magnetic field. So we talked about the atmosphere and how it protects life on Earth by UV radiation, and how it allows that, combined with the effect of the habitable zone, creates the perfect temperature to allow liquid water on the surface of the Earth. But what protects the atmosphere? Well, actually, it is the magnetic field of the Earth. So from this image, you can see that the magnetic field of the Earth is actually very similar to that of a bar magnet or a fridge magnet. We have these magnetic field lines that kind of exit out of the North Pole and enter in from the South Pole. So it's really um, very, very helpful because it protects our atmosphere um, from E&M radiation. So E&M is electromagnetic radiation from the sun. So the UV radiation is absorbed by the atmosphere, but a lot of the electromagnetic radiation is repelled by the magnetic field. And it does this by actually diverting the radiation using the field lines. So if some particle comes in, it actually takes that particle and just kind of deflects it off. It kind of just hits that and just flies away. So it protects our Earth from those charged particles. But what are these charged particles? So the charged particles are mainly, when I talk about like E&M radiation, it's mainly from the solar wind of the sun, which I might be getting too into the topic, but solar wind is basically just a whole mass of charged particles exiting the sun like in a blast. It just blasts constantly, just you exiting the sun. Um, it's a lot of mass, somewhere in like the millions or billions mass, I think, how much exits per second. But that might seem like a lot, but it's only about 1 trillionth of the mass of the sun that exits the sun through solar wind per year. So it's not a lot of mass relative to the sun, but for us, it's a lot of mass that comes hitting at us, and we would not stand a chance. Our atmosphere would not stand a chance against it if it was not for our magnetic field protecting us from that. And actually, another cool effect of the magnetic field and the solar wind is actually the aurora borealis and the um, I forget what the southern lights are called, but the northern lights are aurora borealis. Um, so what the aurora borealis is, and the southern and northern lights both, are actually when you can see how the field lines actually enter and exit from the poles here. So when the particles kind of come in like this, it kind of gets sucked in to the northern and southern poles, and once it does that, it actually hits the gas particles in our atmosphere like hydrogen, oxygen, nitrogen, and once it hits them, it actually releases energy and makes the gas particle light up. So nitrogen maybe turns red, uh, oxygen turns green, something like that. The specific physics behind it is not too hard to understand, but just uh, understand that the solar wind is basically diverted by the magnetic field to go to the poles, and it hits the gas particles. Those charged particles from the solar wind hit the gas particles in our atmosphere, and it creates a light show. um yeah, and whenever there's a lot of solar wind, because the sun is a moving body, obviously. It's not a static body as we thought previously in previous centuries. It's a moving body that's swirling, and it's like a wave, kind of like it's like a turning pot, So it's a moving body, moving fluid body. So it has like a periodic cycle. So when there's a lot of charged particles exiting the sun, you get a lot of aurora borealis and southern lights. So it's actually really, really cool effect from our magnetic field. And the most important thing, obviously, is that it protects us, protects our atmosphere, protects us in transitively. Uh, and so, how did life get started on Earth? We talked about how life is maintained, mainly through these four reasons: how life exists, how it was possible to exist, but how did it get started? So, the best theory that we have right now is that we are aliens. So that means that we did not originate from Earth, which is actually such a cool concept that we are actually aliens, that we have these comets here and asteroids that when I said that heavy bombardment, remember when we talked about heavy bombardment and degassing and how that formed the atmosphere? These bodies like comets and asteroids hit our Earth and during the heavy bombardment. And these asteroids and comets, we have found out that they're actually rich in minerals and nutrients. So when they hit the Earth, they deposit all those nutrients and minerals to the surface of the Earth. And basically, that is our starting point for life. One really important mineral is olivine. It's actually kind of this greenish color, olivine, and that is uh, researchers and astrobiologists have been starting to figure out that olivine is so important for starting life and searching for life on other planets and other places. It's olivine is so important, and specifically stony iron asteroids and meteorites. Uh, some of them have olivine in them, so that's where we kind of connected the dots and said that we're aliens, that we are our ancestral minerals and our ancestral kind of the ingredients for life came from asteroids and comets, and they kind of all mixed together in the early stages of Earth, and it basically was able with that mixed with the water that was created from um, our atmosphere, that all mixed together, and was basically just a perfect storm to create the first single cell organisms. And you know, in the next lecture, we'll talk about how that evolved, obviously, because we are not single cell organisms today, so there must have been something that happened from then now. But yeah, we are aliens, which is such a cool concept to think about. And lastly, we'll just touch on astrobiology, which right now I mentioned it in the last slide, but astrobiology is this branch of biology that's concerned with the study of life on Earth and in space. So how like the study of life basically on mainly Earth and kind of relating it to how kind of connecting the dots and comparing life on Earth with other places. So that's kind of astrobiology, and that's kind of what we've been talking about this entire lecture is basically just different realms of astrobiology. And we will actually, like I said, interstellar and interplanetary life, we'll have a whole other lecture series on this topic because it's such a huge topic and such an interesting topic that we can delve into for a very long time. So we'll save that for another lecture series. But recently, in recent news, I believe it was early March, Perseverance, Mars rover, I believe is the fifth one to land on Mars. So that's so exciting. So what is perseverance and why is it important? So we have, we'll talk about this obviously more in the lecture series, but Mars, we think that Mars could have had life previously. And the purpose of perseverance is to basically find old ancient forms of life and maybe microbacteria, just different small forms of life and the remnants in this place called Jezero Crater, which shows signs of once being a lake, which is really, really cool. That it could have had once had flowing water. Uh, so that's what the Perseverance Mars rover is, and I thought it was really cool to mention in here since it happened very recently, and it's a very cool step in kind of branching out um, our footprint to other areas in our solar system. All right, thank you so much. That is the end of this lecture video. The next lecture we will talk about evolution and how. So in this lecture we talked about how that first micro cells formed. So we'll talk more about how that formed, and we will talk about the evolution and Darwinian theory of evolution, and how we went from being the ingredients for life on a comet and asteroid to being a multi-celled complex human being that we are today. So thank you so much, and I will see you next time.